Okay, so now let's look at the interference of waves, okay, in more detail. Let us say we have a speaker here. Okay, that's producing some sound. And then we have another speaker here. That's also producing some sound. And you happen to be standing here, you know, with full smile. That part is not important, but I like to make that, okay? What do you think you will hear here? Do you think you will hear a loud sound here? Or do you think you will hear only some sound? Or do you think you will hear nothing at all? How do you know what really happens and what you really hear here, okay? Okay, so let's look at the physics behind this, alright? So let us say, let's draw a wave produced by this guy here. I'm going to start here, and then let's say this speaker is, you know, producing some wave, goes like this. Okay, this is what you hear, okay? That's the wave you hear, and then this, let's say, let's also make a, you know, what is this? Let's make this as our origin, this as our some value of x, okay? X, and this is our origin. So let us say this distance, that let us call this as speaker 1, let's call this as a 2, let's call this as a 1. The one closest to you is 1, the farther away is 2. It doesn't really matter as long as we are consistent through this, okay? So this wave, let us call this distance of this speaker from how far you are, let's call this as D2, okay? So this thing is D2, you see? Distance from here, so to this. Maybe I should probably make a distance from here, you know. Actually, you know, I'm gonna make it, no, that's fine. Just this is supposed to be starting here, not like at the end. Well, no, let me change this one. It's important. Here, like that. Okay. So that way it kind of starts from here and then corresponds down here, all the way and goes to 0 here. Okay, so this is the wave that's traveling with the speed v. It has a frequency f and then also has wavelength lambda. Okay, this is the wave produced by this speaker 2. Now this other guy, speaker 1, is also producing a wave of the same frequency and wavelength. This is very important for interference of two waves. It is also producing a wave of same frequency and wavelength. And then let us say it starts right here. Oh my goodness, my diagram didn't. I need to move this diagram a little bit. So I'm gonna move, guys. I'm sorry. This, because I moved this, now I have to move that also to match this guy here with what I want to do. Okay, this is fine. So so this wave starts from here. Okay. So let me see if I can put different color. So this speaker here, it produces a wave of the same frequency and wavelength. That's important. And then it also just goes here like this, perfectly matching with the one that was coming from the other guy. Okay. So important thing here is this. this speaker here, this starts at this distance lambda, wavelength distance apart, okay? So one wave, right, full wave, it has a one wavelength apart, okay? So the difference between these two speakers, this difference. So now, since this speaker is here, let's call this distance from here all the way to the end as a D1, okay? This should be over here just to match. So the D1 is the distance of the speaker 1 from this portion, in this case U, and then D2 is the distance of this second speaker from U, okay, D2. So this difference is really the difference in the distance from this speaker and the distance from this speaker, speaker 1 and 2, right? So that is called a D2, right? The D2 is bigger and then the D1 is smaller, so D2 minus D1. And then we found that this whole D2 minus D1 is actually lambda, okay? In this case, this is lambda for this case, but we give a special name for this quantity where this distance, the difference in distance between the two sources of the wave occur. This is called path length difference. Okay, so this quantity is called path length difference and represented by delta D. Okay, so we have delta D equal to lambda. This is the condition for constructive interference to occur. Okay, so now let us say what happens if we add, if we add one more lambda to this. So add one more lambda, then we'll get what? Delta D could also be lambda plus another lambda. This will give us 2 lambda, right? So what does that mean is, instead of starting from this point here, lambda, we started from 2 lambda somewhere from here. Again, these two waves, then this point is going to sit here and we'll just have the same result, okay? So the result is still the same. This result that happened, whatever you heard, that is due to the constructive interference, okay? So if we keep doing this, it turns out that this path difference D is just equal to m times lambda, where m equal to 0, 1, 2, 3, and so on. Okay, so this is a condition for two waves to go through constructive interference. Whatever you hear will be there now because they are going through constructive interference, which means, the resultant wave you are hearing here is, I could draw it here. I'm not going to draw everything, but let me draw it here. What happens is, just rough sketch, okay? Here you have X, this is origin, then you have something like a bigger wave with the, I don't have a space there, guys. The high amplitude, okay? So this amplitude is going to be really big, right? So by the time you hear here is going to be a sound with higher intensity, okay? So that is constructive interference, okay? So this is the important thing here, guys. Again, the path length difference should be a integer multiple of the wavelength lambda, okay, for constructive interference. One more thing here. So when these waves, they are moving together, they are marching together, they are overlapping and going together, this is called in phase. There is this term called in phase, okay? So here, if I make another one, I have one wave here. If I have another wave here again, or somewhere here, but they kind of overlap and go there, they are in phase. It doesn't have to be just here, they could also be here, like that, in overlap, okay? As long as they are overlapping to each other, these are they are in phase, okay? Meaning they are stepping together, basically. Alright, so that's about the interference. This is for constructive interference. So condition for constructive interference. Okay. There is also a case for destructive interference, so let's see that as well. So please make a note of this. Okay, so I'm just gonna change this position of this second speaker here, okay? So instead of that, let's say this speaker is moved this way. And then we have this coming out, then now this difference here, difference between this, the position of this wave are, let's say, it's not lambda, earlier we had lambda, right? So let's call we have it at lambda by 2 length, okay? So destructive. Destructive interference. So again, let's draw a diagram here. This time I'm going to just make a horizontal line so it's easy for me to draw a diagram. So I'm going to just draw this all the way up to here. Okay. This first one is producing wave. That's not as big as I wanted. So from here all the way to there. Okay, so like that. Okay. Now you see what you hear is up to here. Now this is the wave produced by this speaker 2. Okay. And then let's say this is also moving with the speed v, it has a frequency f, wavelength lambda. But the second speaker here is starting at this is starting at the distance where it's at lambda divided by 2, close to, okay, lambda divided by 2, that's what I wanted to make that close to here. Lambda divided by 2, so now the other wave would start, one started here, the other wave is going to start here. See? Okay, and then now it's gonna go up, go down, and then continue, right, like that. So this is again the wave is traveling with the speed v, it has a frequency f, it has a wavelength lambda. So 2 waves. But the thing is, the difference here is now they are not marching together, they are actually opposite of each other. Okay, so that's the important thing here. And now let us draw, just make our origin here. Let us call this, this is x, this is x, and then let us call this, this distance, again just like earlier, let's call this as a d2, distance of the speaker 2 from you, and then d1 is the distance of a speaker 1 from you, and then this chain length here, right, this difference here, this guy gives us what? Lambda, this is lambda by 2, and then that lambda by 2 is nothing but this is equal to d2 whole length, distance d2 minus d1 gives us this, okay? So d2 minus d1. Alright, so delta D are also path difference for destructive interference to happen. Delta D has to be equal to D2 minus D1, which must be equal to lambda by 2. So what I am saying, why am I even calling it destructive is here. See guys, one wave is just going like this, this other wave is going like this. These two waves are wave out of phase, okay? Meaning they are not marching together, okay? They are actually opposite of each other. So what happens is, look at this. If I were to draw, by the time the wave reaches to you, you will get something like this. If we were to make it, you would have this. The wave you would get is really the resultant wave would be wave with 0 amplitude. Okay? So they they look like they cancel out each other. So what you hear is nothing. Okay? So you would be in a really quiet space by the time these sounds comes to you. You won't hear anything. Okay, so this is called the destructive interference, and the condition for that is, for now we are writing the path difference delta D is equal to lambda by 2. What do you think would happen if we add delta D equal to, let us say, add lambda? What happens? Delta D is what? Lambda plus lambda by 2. Okay, this is what? 1 by 2 lambda, right? Meaning, what does it mean? Adding lambda means this thing, we have it here, but let's move it instead of here, right? Lambda by 2, let's move it somewhere around here. Now I don't have a space here, but if we are to move this, have this lambda by 2 plus one more lambda somewhere around here, what happens is this resultant doesn't change. You will still have destructive interference at the end here, okay? The resultant would be the wave will travel with 0 amplitude basically, or there is really nothing, right? So it turns out, so look at this, if we keep doing this, we can generalize this one, and then we can write delta D equal to m by m lambda by m plus half lambda. Okay, so this is the condition here, or mathematically we arrive at this condition where m equal to 0, 1, 2, 3 and so on. So you see here, this is the path difference. Path length difference is not just the the integer multiple of wavelength. Now it's m plus half times lambda, right? So this is the important thing. So for destructive interference to occur, the path length difference must be the multiple of this quantity here, m plus half. Okay, not just simply the wavelength. All right. So that's about the destructive interference. And again, remember, in destructive interference, the waves, they are out of phase. So by the time this waver is standing here, the person hears the wave, is really there is nothing to hear. So that's really, the sound would be really minimal at that location. Okay. So what does this really tell you? Well, for us to, for us to find out whether we'll hear sound from, two sources is really determined by this different path length difference, meaning how far these two sources are, and of course where you are at, right? Those values are determined based on the distance from the person who is, standing away from the sources, and then also the wavelength of the wave. Okay, so please go ahead and make a note of this.